I'm going to do a quick, you know, real quick lecture on complex ion equilibria. It's very similar to everything we've done so far, so I'm just going to talk about it real fast and go over one method that might change ice table problems a little bit, but this is just to introduce it. You might see it on a practice exam example or something like that, but the idea is the same with everything else we've done before. And then after that, we're going to continue with finding our unknowns, which is the exact same procedure we did last time, so we should be a little familiar with that. And you're going to have one of three unknown solutions. I have the key for what ions are in that right here. So we're going to go through this pretty quick. All right, so complex ion equilibria. This is basically any equilibria that involves a transition metal, right? And it's called complex ion equilibria because these transition metals, what they do, like let's say we have titanium or something like that, they have these funky looking d orbitals, right? And these d orbitals, if you guys remember, is where you get your octahedral shapes, some more complex shapes from Chem 101. They can basically bind to ligands, and those ligands can be molecules themselves, something like this, and they form these transition, complex ions or transition metal compounds, or we can also call them coordination compounds. And the reason they're called coordinations is because they don't really involve sigma or pi bonds like traditional molecules do, their covalent interactions. They use these d orbitals and they form what are called coordination bonds, right? So they're slightly different. They still, everything in chemistry is still sharing electrostatics or electron density, but it's a coordination bond. It's not really a like single or double bond that you would look at. So these are called coordination compounds. And so in aqueous solutions, water molecules act as Lewis base to donate electrons to the transition metal, right? So, the water molecule has something that looks like this, right? And these lone pairs act as Lewis bases. And we'll talk more about that when we talk about acids and bases. When they donate these lone pairs to the MTD orbitals of these transition metals, right? So they donate these lone pairs and they form these complexes. And so, for example, silver ions, they get hydrated in water to form AgH2O+. You still have a positive charge on this ion because you haven't really donated any single electron, right? You're coordinating this compound to the MTD orbitals in the transition metal. So the silver still has a +1 charge because you haven't neutralized that charge in any way. And the fact that it has this, positive charge means that it usually interacts with light in a different way. So a lot of these compounds tend to be colored and very pretty, like we saw with the potassium permanganate. Remember that was the first lab we looked at? That was a complex ion, and that was a purple type color, and you guys did your study to use that to analyze the kinetics of that reaction. And so that was actually the kinetics of a reaction with complex ion formation. And so we often just write Ag plus as a shorthand notation for this because this just happens naturally in water, right? So this just happens naturally, and so the ions do not actually exist by themselves in solution, right? So the Ag plus ion does not actually just exist as Ag plus floating around in solution. Usually it exists as a coordination compound coordinating with water molecules. And so the metal has this kind of electron density associated with it, and then you have these different kind of coordination compounds that can bind to it, and that affects the electronic structure of the atom, and that electronic structure is where we see light. So if you guys remember, when things get excited in molecules, the electrons get excited, and when they decay, they release light, and that's how you can look at how molecules and atoms can absorb light. And later in the semester, we'll actually go through how to calculate, what is the color of this compound based off of just looking at what's the metal and what's the molecule that's binding it. And so these complex ions usually contain one or more ligand is what we say. That's what we call these molecules that bind them. And a ligand is going to be, most of the time it doesn't have to be, it can be a neutral molecule or ion that acts as a Lewis base. And a Lewis base, does anyone remember what a Lewis base is? It's an electron donor, right? So if something has lone pairs, usually it acts as a Lewis base. It's an electron donor. And so what happens is if you have a stronger Lewis base, right, one that acts more basic than the one that's just present as water in solution, what happens is that will replace or take the spot of the water in solution, right? So if we have just Ag, that's why we usually don't write the water molecules with the Ag plus ion, because if we add ammonia, for example, then that will replace the water molecules in the coordination compound, and then the water molecules kind of just cancel out on both sides of this reaction, which is why we usually simplify this reaction. I just wrote the box here because all of the files right here got corrupted. So that just showed a bunch of funny symbols there. So the white boxes here don't mean anything. Those are always just going to be, equilibrium arrows that are going in both directions. And so, yeah, see, here's the funny symbols that show. I don't know how that happened. So for simplification, usually we don't write the water molecules there, right? We can write the water molecules, but they kind of cancel out on both sides of the reaction. They don't really affect the equilibrium at all. Why doesn't water molecules affect the equilibrium of the reaction? Because it's a liquid, right? H2O is a liquid. So it doesn't affect the equilibrium position of the reaction, right? So all that matters is the concentration of the silver and the ammonia in solution, and that is the formation of this complex ion, right? So water molecules don't really affect the position because it is a liquid, right? And liquids don't affect the state of matter unless you're at very, very low concentrations. And so, like I mentioned, these complex ions tend to be relatively pretty, right? So we have nickel that's dissolved in water, this complex ion. What happens is, and what we're gonna talk about is, not for a while, it's called crystal field theory. Crystal field theory. And what happens is, these ions, they have their own electric field that goes out. You add the ligand here, and depending on the ligand, that has its own specific electric field. When those two electric fields interact with each other, they distort each other. That distortion of the electric field determines how the molecule interacts with light. How it interacts with light tells us what the color is going to be, right? So all we did here is we replaced the water ligands in this coordination compound, and it turned from a green color with ammonia, and now it turns a nice purple color, right? And so that color you're seeing is directly related to the distortion of the energy levels within this molecule. And that distortion, in a simple way, is just two electric fields that are interacting with each other. Why? Because molecules and atoms are made up of electrons, protons, and neutrons, and determined by electrostatics. And so the equilibrium constant, right? So I know we have a lot of K variables. This one is called the equilibrium formation constant. And so if we looked at the previous reaction where we had Ag plus 2 NH3, this goes to Ag NH3 2 plus, right? That was our reaction here. The equilibrium constant is the same thing as what we've done, everything we've done before, right? These are all aqueous in solution, and we just do the products over the reactants. This is called the formation constant. And so all of these are going to be in the aqueous phase, right? Where KSP, we're looking at the process of dissolving a solid, right? So the reactant was a solid. Here, everything is already in the aqueous phase, so we have to include all of these concentrations in our expression for the equilibrium, right? And so I'm just giving you guys an idea of what KF represents, but if I gave you this reaction, right, this first reaction here, AQ, those are all aqueous. You guys would know to include all of them because they're all in the aqueous phase, right? So we know that just based off of our principles of equilibrium. And so these specific values, right? So we looked at solubility, those values, how did they, what were they generally, large or small, the values for solubility? They were small. They're all like much smaller than 1, right? Because things aren't generally just going to dissolve completely into solution. They just tend to not have large solubilities like that. Complex ions, on the other hand, if we look at them, they're all values 10 to the 21, 10 to the 33, right? These are massive compared to, almost like larger than, if we were looking at meters, larger than the observable universe, right? So these are very, very large values. So these are large values, which indicates that the formation of these compounds, complex ions, is extremely favorable. And so this is kind of the intuition that leads us to how to solve complex ion equilibria problems, right? So these are going to be extremely favorable. And that's why when we're doing our qualitative analysis, we use the formation of complex ions to make something more soluble in solution, right? Remember last time I had those 3 reactions, and like if I put this formation of this complex ion in there, it causes a chain reaction of all the reactions to force our solid to dissolve into the aqueous phase, right? So complex ion formation is used a lot to force things to dissolve. Why? Because they're all in the aqueous phase, right? And we just saw that from the previous slide here, right? All of these all of the reactants and products are all in the aqueous phase. So if we want to dissolve something, generally the use of the formation of a complex ion is helpful for that, right? And so when we're solving these problems, you use something called kind of the bounce back method. When you're looking at a solution where you mix these 2 things together, you assume first that all the reactions and all the reactants come together to form the complex, right? So you assume everything comes together to form the complex, and that gives you your initial concentration, right? This gives us initial amounts of everything. Then after you've assumed that all the complex ion, and this is because the formation constant is so large, you assume that basically dominates the equilibrium process, that's going to push everything towards the products or the formation of the complex ion. Once you have those initial amounts, then you use some, now we know some of it's going to dissociate because of equilibrium, it's going to bounce back, and you're going to put a little bit of the individual ions in solution again, right? And this is, in step 2, this is where we use, what do you think we'll use to determine the concentrations of these things at equilibrium? What tool have we been using to determine concentrations at equilibrium? Ice tables, right? So this is where you're going to use the ice table, right? So step 1, you use to determine the concentrations at equilibrium, or your initial concentrations, because you're assuming that all of the complex ion has formed. And then in step 2, you're going to use an ice table to then determine what the equilibrium concentrations are going to be. And so I'm not going to go into, when you guys mind muting that for me for a second? Thank you. And so the first step, we assume that we're going to make as much as we can of the copper ammonia complex ion here. So the way we're going to change on equilibrium is we're going to move, and you could do this more qualitatively if you, instead of making a guess as to which one you're going to consume completely, you can use what's going to be the limiting reactant, what's going to be the use the limiting reactant to determine what's going to be depleted completely, but you're going to use all of your copper ion in solution. For every mole of copper we lose to the complex ion, how much of the ammonia should we use? 4 times that amount, right? So our change is going to be 4 times 0.015. And then how much complex ion should we make from that? It should be a 1-to-1 ratio of copper to the complex ion, right? Because the stoichiometric coefficient for the complex ion is 1. So this is going to be 0.15, right? And so we use this to get our equilibrium values. That's going to give us 0.040, and this is 0.015, right? And so these are going to be used as initial values, right, for our ice table. And the reason for that, technically we don't have to do this, right, bless you, because we know that we can do everything from equilibrium by flipping equations around and stuff, we can modify our equilibrium constant, but this is an easy way to solve the complex ion equilibrium problems. So these are going to be used as our initial value, and then we say we create all of the complex ion, and then a little bit is going to bounce back into the products and the reactants, right? So we use those as our initial values. So this is from step 1, and again the justification is because the formation constant is really large. And so now we're assuming that things are going to move back in the opposite direction. And so now we're going to use values of x to then solve for the equilibrium change, right? So we're assuming that things are going to bounce back the other way, which means that we're going to be moving the reaction to the left here, towards the reactants. If we're moving the reaction towards the reactants, then what should be the sign for everything, starting from left to right? For copper, should it be positive or negative? Positive, because we're adding that. For ammonia, should it be positive or negative? Positive. And then what about for our complex ion? Negative, right? And then we know for every 1 mole of this that we lose, right? There's no coefficient there, so we just do minus x. Then how many moles of ammonia do we gain? 4, so it's plus 4x. And then for copper, it's a 1-to-1 ratio, so it's plus x. So we get x 0.04 plus 4x, and then 0.015 minus x. Right, and now these are going to be our equilibrium concentrations that we can use to solve for the equilibrium concentration of copper ions, for ammonia concentration, and so on. Right, so how do we use those equilibrium concentrations to do that? Right, what's our relationship between the equilibrium concentrations and the formation constant? We have Kf. What's Kf equal to here? NH3, 2 plus, over Cu, 2 plus, and then NH4 to the 4th power. NH3, sorry. Like that, right? And we just plug these values, these equilibrium values, in here, right? So these are equilibrium values. These get plugged into there, and we get something like 0.015 minus x over x times 0.015 minus x, sorry, plus 4x, sorry. 0.04 plus 4x to the 4th power. Right, so at this point, you've done all of the chemistry work for the problem, right? You've done all the chemistry work. We've set up what we know about equilibrium to be true about these concentrations at equilibrium. And so you're just going to plug these values in to then solve for x. Here we have something to the 4th power that tells us we probably need to use what to simplify the problem. Or if we have something to the 4th power, you know, we don't have the tools to find a quartic equation, right? So we're not quadratic, we're not cubic, we're quartic, right? We're going to use something to simplify, most likely an approximation, right? So that's how we would end up solving this problem. The justification for that is we're talking about the reaction going in the opposite direction, right? Which means that our concentration of this is massive compared to these, right? So if we're shifting in this direction, then this change as we move towards the reactants, which should be very, very small, should also be small. In this case, you know, if this is like something like 10 to the 33, this will be like something like 10 to the minus 20 or something, right? 0.04 is 10 to the minus 2. That's almost, you know, the difference between the size of a subatomic or a subnuclear particle compared to us, right? So this is a huge difference in values between us. So we just say, okay, 0.04 plus 4 times something to the 10 to the minus 20 is basically 0.04, right? So that's the justification for that. We aren't going to go through the math to solve this right now, but I wanted to introduce the idea of complex ion equilibria. We'll go through some more examples and probably see something on the practice exam related to this, right? But this is the same, right? It's the same setup. I want you guys to start seeing that when we do this for gases, just regular aqueous reactions, solubility of products of dissolution and now complex ions. And then next week when we start talking about acids and bases, these are all just the same idea of looking at equilibrium concentrations, right? This X value just represents the change on the way to equilibrium. I start